August 2017, we're looking at the constructed response, part 2s. And so those are worth 2 points each, which makes a difference in how much we write. Now, two cylinders have equal volumes. This is Cavalier's principle. We've seen this a couple times on different exams. Basically, what we're saying is so if two figures, two 3D solid figures, have the same base area and the same height, then their volumes are the same. So you could actually have, a rectangular prism and a cylinder have the same volume in the right conditions, as long as their base areas are the same and their heights. Now, a lot of my students went a few different ways here. Good things, they actually calculated both volumes and showed that they were the same. That's fine. If you didn't know Cavalier's principle, you could do that. There's nothing wrong with that. So they completed two volume formulas. They talked about the 12 being the slant height, which is not the actual height. The actual height is perpendicular to the base, not at a strange angle to the base. So you talk about a number of things, okay? You do have to explain, so that means use your words. Make sure that it's not just formulas and calculations, okay? That's what we're going with, is that whenever it says explain, there should be sentences. Now, how do I show? Basically, my job is to show that the base areas are the same. So it's going to be pretty simple. Okay. For both cylinders, the radius is 5. Okay. Diameter of the tilted one is 10 meters. Half of that is 5. Okay. So the area of the base once they have the same radius, they have the same area. Now, talk about the height. The height for each of them is the 11.5 meter number. The 12 meter is the slant height. But we don't use that to calculate volume. Same base area and same height gives us equal volumes. Okay, good enough. If you actually want to go calculate them, you can, not necessary though. All right, So in the diagram, the rhombus, okay, pretty common problem. If they give you the length of both diagonals in a rhombus, what you need to know is these are the properties. First, diagonals of a rhombus bisect each other and are perpendicular. So let's apply that. So if PR is 16 and P to T is 8, there's a right angle there. If Q dash is 30, Q to T is 15. So what we end up having is a Pythagorean theorem problem. So we'll go 8 squared plus 15 squared equals T squared. That's 289 square root, and we get 17. Okay, so now each side of the rhombus, since the sides are all the same for a rhombus, each side of the rhombus is 17. So perimeter is 17 times 4, which is 68. Okay. Describe a sequence of transformations that can map quadrilateral math onto math double prime. So personally, what I would probably do is rotate math centered at the origin by an angle of 180 degrees. Now I would actually go and graph it to show more work. Okay, where does M land? So M prime is right here. H prime stays. T. That doesn't seem right. Something is off. Whoops, right here. Okay, we're good. So T, that's T prime and A. Right there. Prime. So we have this. Now what we would do then what we would do next is now translate that image up 1, left 1, okay, 2, map onto M, A, T, H. Anything else? So it's a two-pointer. I think the work would be to demonstrate this, fully describing them. I think that's going to do it. Pretty set. Okay, so compass and a straight edge. What I'm going to attempt to do is there's a couple ways to do this problem. Hexagon and equilateral triangle are done the same way. You would take your straight edge, pick any diameter, just have to go through the origin, or the center, sorry. Okay. And now what I would do is I would put the center of my compass tool here. I would pick a radius that passes right through there. Okay. So what you end up doing is you end up drawing a half or part of a circle, a little more. Okay. Where it's going to hit in these two locations. Then you're going to do the same thing here. Put your compass tool there. Okay, you're going to draw that arc, and what we get is we'll get 6 equally spaced points along that circle. It doesn't look like it, but that's because I'm not using a right tool. I'll head over to Geometry Sketchpad and actually do this the right way. Okay, over here on the best I can do with this is put it on Geometry Sketchpad for now. Okay, so I've got circle O. I pick a random point on the circle. I'm going to draw a straight path over to here till it hits, and then that's going to be, I actually don't need that segment. I'll just use those locations. Actually, yeah, I probably, as far as work goes, I should show that. So I will. Then we'll just hide this. Okay. Now the next thing is I put the center of my compass tool there. Okay. I'm going to find the radius that will give me a circle that goes right through the center. Now I'm going to display that in dotted so you can see the difference. So the original is this one. So what happens is I make this one. You only have to go, you don't have to go the whole way. You know, just draw the part of the circle that actually crosses and then go a little past. Here's what just has happened. Now we have 3 points that are all the same distance apart. Okay. Or actually these two are the same distance and those two are the same distance. Now I'm going to do the same thing. I'm going to take my compass tool, I'm going to put it over here. I'm going to open it up to the radius that goes through there. It should be the same radius. Construct that circle, and now we have another 2 points that we found. If we connect all 6 of these points, we create a regular hexagon. A regular hexagon has all angles the same as each other, and then it also has all sides the same as each other. So that's what it's going to look like. I don't know if we have to label it. No, it doesn't really say, so that's good enough. And this is a rough sketch. It's the best I can do. There is another way to do it. Come see me if that's the way you want me to show you. But this seems to be really efficient. Continuing, though, if you were to need an equilateral triangle, just do every other one. Right? Just skip one in between. So use these 3. Okay, so the regular hexagon construction takes care of you know, the equilateral triangle as well. Almost done. We'll probably stop after this one. So the coordinates of these points, okay, so good. All right, we don't have to construct this. The use of the graph below is optional. Basically, we could calculate the length of AB. We don't actually even have to graph it, and then cut that in half. Because after a dilation of a half centered at the origin, A prime B prime is going to be half as big as AB. So let me just get those graphed. I'll pause it and graph those. So there's AB. They made it so it's not really nice. I actually will probably, I could do it either way, right? So up and down from here to here is across 2, up and down 3. Cut that in half right there. That's A prime. If I go over to here, it's 1, 2, 3, 4, 5, down 1. So go 2.5, half. There's B prime. All right, so that's not going to be pretty. Let's just use the length of AB and then cut that in half. So from A to B, the change in X is 3. The change in Y is 4. So what we would do for the length of AB, oops, sorry, length is going to be 3 squared plus 4 squared equals, we'll call it D squared. So then 25 equals D squared. Square root of 25 is 5, right? Now, be careful, that's the length of AB. we need to dilate by half and give me the length of A prime B prime. So A prime B prime, length is half the length of AB. So A prime B prime is half of 5, which is 2.5. All right, good enough for this video, and I'll finish on the next one.